make sure everybody's wide awake for this.
Thank you.
This story takes place about 12 miles north of Wikia, so everybody knows where that thing is. I got interested in Big Sandy in 2009 when Bell Copper was exploring about 20 miles further north on our old Cauba project. We call that Perseverance now. We were having some technical success drilling through gravel out in the bottom of the valley. We had drilled about 1,000 meters of diatreme breccia with sulfides in it. And I said, if this thing is working at Perseverance, we used to call it Cauba. If it's working here, it should work further south down the valley on the Diamond Joe porphyry. So just based on that, I wandered out into the valley about where I figured the top of Diamond Joe should be sitting. And like other geologists before, I noticed the gravel out there was strongly tinged red, stained red with hematite. And a shareholder of Bell Copper just a couple of months ago shared this quote in the upper left with me. It's not much, but it's absolutely what we're looking at in this slide right here. It was Jim Sell writing a memo to Hal Courtright in 1969, just a comment on the Cane Springs occurrence. And Jim writes that a red conglomerate is conspicuous in an area of gray conglomerate. What is the cause of the red area? Well, I think Bell Copper is beginning to unravel that mystery. There's a porphyry copper down there, and I hope by the end of this, you'll see some of the evidence that makes Bell pretty confident of that. I want to start out by telling you that everything I'm about to say is a lie. I'll be using a lot of forward-looking statements, and you gotta appreciate that those are things that I have no control over. I can't make them come true just by saying them. Footnote one tells it all. Nothing that I do guarantees we're going to have something that'll turn into a mineral resource. And if you pay heed to Mark Twain, who said a mine is a hole in the ground owned by a liar, that would be me. If my lips are moving, don't pay attention. All right, the Big Sandy project is one of two properties that Bell Copper controls. The first is Perseverance up 15 miles east of Kingman, out in the Big Sandy Valley at the northern end of it. Big Sandy is another truncated or bolted off porphyry copper prospect. And we're looking for the top of Diamond Joe. Diamond Joe Peak, which has been explored for many years as a porphyry copper deposit, is the bottom of a porphyry system. And one observation I've made there is that the guys who drilled it for decades and decades, from the late 50s into the the mid 80s, should have pointed their drill up rather than down. They were underneath where the copper shell would form. They were down in the hot magmatic hearth of the system, and the cooler regions of a porphyry copper system where chalcopyrite is prone to precipitate would lie a couple of kilometers above the level of the exposure of the Diamond Joe system. So it's that piece of rock that I'm looking for. I've been looking for it up at Perseverance and have gained a lot of confidence that Perseverance is out there. Likewise, in the same general area, east-northeast of Diamond Joe Peak should be the top of the Diamond Joe system. And so just based on that geological concept that porphyries are zoned from hot copper poor magmatic regions into cooler, more copper rich regions in the upper parts, just based on that idea, Bell went out and staked some ground out in the Big Sandy Valley. The first work that Bell did out there was in 2009, again after we drilled the diatreme breccia in our drill hole K9. Far out, 7 kilometers out from the range front, out in gravel that other geophysicists believed was 4,000 feet deep. We demonstrated it was more like 2,000 where we were drilling. And as we've moved to the east-northeast, that gravel is now 200 meters thick within the realm of open pit mining. We're working in elephant country. Bell only has 2 projects. There they are right there, the 2 red stars. We're in between Baghdad and Mineral Park. We're in elephant country. Arizona has produced 10% of every pound of copper in existence in the world, in spite of 80% of the state being covered by sand and gravel and post-mineral rocks. Our belief is that that 10% ought to be just the start on Arizona's ultimate copper endowment. And so looking for truncated porphyries is what we've spent our time doing. We're not off in jurisdictions of the world where you may not be able to keep what you find because of nationalism or other issues that make exploring in other parts of the world more difficult. We know Arizona, we know how the laws work. We got pretty good laws, at least we have had in the past. The jurisdiction of Arizona is probably the best in the world for finding a new mineral deposit and having a good chance of turning it into a producing mine. So that's where we work. It's a prospective area. We're on a trend between the Baghdad, where Freeport makes 200,000 tons of copper a year, and Mineral Park to the northwest. Origin Mining has that on care and maintenance, but there's a 50,000 ton per day flotation mill sitting there waiting to be fed again. And further down to the southeast is Resolution. So Bell has two projects on prospective ground in elephant country. The measure of thing looking for comes from being able to see the bottom of the system. We got 2 of these, Big Sandy and Perseverance. Both of them are exposed back in the Wallapai Mountains. We can put our boots on those root zones, those bottoms, and map them. They've been mapped by other people fairly well. We can measure the dimensions of the mineralogical features related to them, like the pyrite shell. That's just a very crude distribution of sulfide minerals in and around the porphyry intrusion. At Big Sandy, that pyrite shell is 5 kilometers by 6 kilometers. At Perseverance, it's 5 kilometers by 3 kilometers. We don't have any resource. We don't have tons in grade. But if you compare the dimensions of that pyrite shell to other big porphyries in the world, our targets are just as big. The ore body at Escondida rattles around inside the Perseverance or the Big Sandy pyrite shell like a marble in a tin can. What we are chasing has the dimensions to become a world-class system, or to contain a world-class porphyry copper deposit. And we just got to get out there and drill it and find out what the copper and the moly grades are. Certainly the tonnage is there, it always is, but we got to find the grade. And I think we're on to it. The concept is that the roots, which are exposed to the left, this you folks see my mouse? I'm circling a red outline there that represents the roots of the Diamond Joe porphyry stock. You can see just a fantastic array of radial and concentric vein sets that surround the apex of the Diamond Joe system. There is a molybdenum resource that's been drilled out there in the past. It's just a spectacular patch of ground. If you're learning what a porphyry copper looks like, you can go there and see all the features of a porphyry copper deposit, minus the copper shell. That occurs at a higher level. But again, the idea is that a late post-mineral basin and range normal fault with a fairly shallow dip has truncated this root zone and carried the upper part of the system, the copper-bearing part of the system, east-northeastward out into the valley. In fact, at Big Sandy, east of the Big Sandy River, across the midpoint of the valley. And so our concept is that the top of the Diamond Joe porphyry system now lies about 13 kilometers to the east-northeast of the root, underneath an unknown thickness of sand and gravel. what one sees when you wander off to the east of 93, this is Highway 93 here, Wikiup's down to the south. This is Cane Springs Ranch. What you see when you wander off the east side of that highway is these gravel deposits stained bright red. It's clear there's a lot of exotic hematite, very much like the flanks of Red Mountain, south of Tucson in Arizona. There's been a lot of sulfuric acid carrying dissolved iron from an oxidizing pyrite shell out of a porphyry copper system. That iron is accompanied in some areas by exotic copper, and it was finding some of that exotic copper 11 years ago that got me interested in the Big Sandy area and kept me going back. Diamond Joe is important. It's the stump of a big redwood tree, and nobody goes out to make redwood lumber by digging at the stumps. The stumps are interesting. They're evidence that there used to be a redwood tree there. Here's the stump of our redwood tree. We can go in, we can sample it, we can taste it, we can sniff and scratch at it, we can sample its DNA and prove that it's a redwood tree. We can count the rings. We counted the rings there at Diamond Joe Peak. Our redwood tree is 72.9 million years old. So we know it's a redwood tree, but again, you don't go running a stump through a lumber mill to make lumber. You got to have the trunk of that tree, and that's what Bell has been pursuing, is the upper prospective copper bearing part of this system that had roughly the dimensions of a big redwood tree, much taller than it is wide and broad. But the stump tells us everything about the system. It tells us what minerals flowed up through the cracks, what the orientation of the cracks were, which part of the stump might be more favorable. And we use that as a guide to explore undercover. We know what the alteration pattern should be by mapping the alteration pattern around the stump. It should be mirrored, it should be reflected up in the hanging wall piece of that system. So if you get up on top of Diamond Joe Peak, you find intense Grison style alteration. This is really sericitic alteration gone crazy. There are muscovite flakes 1 to 2 centimeters wide. You know, normally you look at sericitic alteration in a porphyry copper system, you're looking at it under a microscope, under cross polarized light, and you can see these flakes of mica that grow in sericitic alteration. In the deep roots, the quartz veins are thick and white, milky quartz, and the sericite has become so coarse grained that you can properly call it Grison. There's a lot of molybdenum. Molybdenum drops out in both the hot and the cool parts of the porphyry system, and molybdenite is quite common in the root of the Diamond Joe stock. In fact, there's a sub-economic molybdenum resource that was drilled out by, I think it was mainly Arkansas, Louisiana Gas Company, ARCLA, back in the late 60s and early 70s, right up on top of Diamond Joe Peak. Inspiration Copper drilled up there in the 50s and 60s. The Leviathan Mully mine produced molybdenum. I think it mainly went to the Germans in advance of World War I and World War II, where they turned it into armaments and sent it back to us. Let's see. Gulf Minerals was probably the most recent modern exploration effort on Diamond Joe Peak. Joe Wilkins worked on that between the late 70s and mid 80s. And as recently as 2010, Freeport-McMoRan got back and did some drilling around the old Leviathan molybdenum mine. But there's lots of copper up on top, lots of azurite and malachite, black copper wad. And if you get down into the veins, you see gobby chalcopyrite in places and a lot of molybdenite, very big veins. Some of these veins are 3 meters wide and can be traced for 1,000 meters on the surface. So it's very clear from looking at the Diamond Joe stock that billions of tons of water flowed up through that porphyry stump. And that water went up because it was hot, and it is the receptacle, it's the the point of deposition of all of that water that I want to spend my time drilling. And that point I now believe to be 13 kilometers offset from the route to the east-northeast. The hanging wall target, we first started exploring that, Bell did, back in 2009 after drilling our K9 drill hole at Perseverance and just saying, hey, the model is working at Perseverance. Perseverance is where Bell has a joint venture right now with Cordoba Minerals. That's a Robert Friedland company. Robert's really excited about Perseverance, and they financed our last drill hole there, K20. The model is working at Perseverance. We're very close to a porphyry copper system. We see everything that a fellow wants to see next to a porphyry. We've got A veins and B veins and D veins and chalcopyrite and bornite and molybdenite. So it's clear that the amount of offset on this Wallapie fault that's truncated the porphyry system, both at Perseverance and down here at Diamond Joe, is relatively flat line and has caused more horizontal displacement than vertical. And unfortunately, we proved that by drilling back in 2011 on the Big Sandy. We didn't move far enough to the east. We drilled a couple of holes through 3,000 to 4,000 feet of conglomerate without ever getting into the bedrock. In the intervening time, we've done more exploration at Perseverance, and my concept of where the thing ended up has moved further east. So now it's mainly east of the Big Sandy River. But this property was initially optioned to a company called Phoenix Copper. Phoenix, drilled the first 2 holes and then allowed the claims to lapse in 2013, and the thing went dormant for about 10 years. This is what you find when you drill holes into the gravel out there. You find that the cobbles and pebbles are sometimes coated with native copper, very much like the whitetail conglomerate out around Resolution, where the post-mineral gravels are mineralized with exotic native copper. Another thing that we found once we started looking in the right area were faults cut up through the gravel. So these are post-gravel faults that are glued together with this black stuff. And the black stuff is copper wad. It's copper manganese oxide that forms a cement to the gravel. And so the faults in some places stand out in relief, glued together with this black copper wad, neodicite. And that material right there runs about 1% copper. So it's clear there's a source of copper out in the bottom of that valley, actually on the east side of the Big Sandy River, source of copper that's created by oxidation of pyrite, natural in situ leaching of a copper shell. And then just because the hydraulic gradient there is up and out of the formation, it brings that dissolved copper to surface where it can glue the gravel together. Bell was kind of disappointed with the speed at which Friedland and Cordoba Minerals pursued our Perseverance project to the north. They kind of put it on ice during the COVID pandemic, and Bell didn't feel much like something to happen up there. So let's go take the next one and pursue it. In the meantime, there's not a lot of people out there to catch COVID from, so seemed like a good place to hang out. So early in 2020, we went out and staked the area, a little bit on the west side of the river, a lot on the east side of the river, and kind of refined our target area. Once we got out on the ground, we started finding cobbles and boulders with chrysocolla and chalcocite and interesting stuff like that. So we drug that into Skyline Labs, and Nancy was more than happy to run that through the lab, and we got a couple of plus 1% copper assays out of pieces that are very clearly derived from a supergene enrichment blanket. It's chrysocolla and second stage or late stage chalcocite that have been transported only a short distance from their source. They've got very angular corners. They haven't come all the way across the valley. And there's a giant pile of fanglomerate deposit. This dark brown deposit here is made up almost entirely of pieces of a weathered porphyry copper deposit. So there's evidence that that there really is something out there, copper leaking out of the gravel, and porphyry copper pieces in a fanglomerate. So we hired Quantech to come out and run a magnetotelluric survey, a conductivity survey over the area. And lo and behold, they turned up a very large electrical conductor that extends deep into the subsurface. Based on that work, we got out and began drilling in October. Now, I encounter a lot of resistance when I start sharing these ideas with other geologists. Geologists have the idea that things can't move that far. Faults, flat faults are not really flat, or at least they're not active when they're flat. Here's a very recent piece of research from this is out of Nature Communications, December 2020. I want to focus on this panel on the upper right that looks like an electron microscope image of a fault surface. You see, it looks like a slickened side with some striations going down it, and you can tell the movement on that surface would have been from northwest to southeast. What this picture really is a high-resolution seismic reflection survey covering about 1,000 square kilometers in the South China Sea. This is an active, low-angle normal fault that dips at about 6 to 10 degrees to horizontal and has accommodated 35 kilometers of slip. So if you've ever seen a landslide with a house on it, you know, sliding down across the countryside at a very low angle, it's clear the Earth can have flat faults that produce a lot of horizontal displacement and very little vertical displacement. As long as there's a little bit, gravity will drive the offset. There are modern examples in New Guinea and in the Aegean Sea. So these things are real. We think we have something kind of like it at Big Sandy. Another example of movement that has happened at Big Sandy, and I don't know that this has ever been described before in Arizona geology, but I'm referring to it as a Quaternary catastrophic fan collapse. And the evidence of this fan collapse, this is a Google Earth image looking obliquely across the Big Sandy Valley. Here's Highway 93 coming down here. Wikiup would be to the south, Interstate 40 further to the north. And what's clear is these giant fans that are common in Arizona. They're referred to as the Cordonez surface, dated about 1 million years ago. The type locality for the Cordonez fans is up in Oro Valley and Catalina, coming off the Catalina Mountains. But that surface is you know, you see it all over Arizona. At our project, that fan is missing. There's a giant hole, a giant amphitheater, where that entire fan surface has disappeared. And the fans themselves collect boulders that wash out of the adjacent mountains. Some of the boulders are giant, five meters across, and those boulders generally stack up pretty close to the apex of the fans. But at Big Sandy, we find boulders 2 to 5 meters in diameter in this patch of ground way out in close to the Big Sandy River, and a gap, an amphitheater, where that fan is missing. You can clearly see a vertical scarp that cuts this fan system. This is the fan here, this surface here, and it's missing. It's entirely missing and forms a vertical scarp. The scarp points downhill, down into the bottom of the valley. Another scarp across this boundary is not visible because of the way we're looking. But these giant boulders, which would have deposited very close to the edge of the fan up in this area, are now out in a pile on our project area, stacked up in this place here. And it's actually kicked the course of the Big Sandy River further to the west, where the river's been forced to flow around this catastrophic landslide that moved the million-year-old Cordonez fan out into the valley bottom. But again, all of this has happened just because we get our boots out on the ground and get to looking at the rocks. You can see that copper-bearing fanglomerate, that kind of particularly iron-stained patch of alluvial fan right in that area there. And we've now found chrysocolla and chalcocite-bearing clasts for a belt about 6 kilometers north-south, extending across this area. So another thing we've done is to correlate boulder types in the gravel. Now here is a correlation of a boulder. This is probably the Aquarius granite from an area here on our property. We found the source, or are getting closer to finding the source of that material way back on the west side of the valley. So there's no way that some ancient river was washing out of the Wallapies, crossing the center line of the valley, and flushing these cobbles and boulders back up the other side of the valley. The easier interpretation is that the boulders rode on a fault as an intact mass in the hanging wall of a fault, and slid all the way across the valley, taking the top of the Diamond Joe porphyry system with it. So we got out on the ground, we staked our claims, refined the target area by just walking around and looking at rocks, ran our magnetotelluric survey, and then in October started drilling. Here's the Quantec guys out on the ground making magnetotelluric measurements. Showed us we had a very electrically conductive mass extending deep into the subsurface, deep underneath the gravel. Here's a three-dimensional depiction of what that thing looks like. 3.5 kilometers east-west, 2.5 kilometers north-south. It actually extends further south off of the area that we initially surveyed. Based on this, we extended our land package by staking to the south. Here's the copper-bearing fanglomerate off on the east side. So we've got a large conductivity anomaly that we just had to know what was causing it. So again, here's our exotic copper. We're looking for the source of that copper underneath cover. Here are the pieces of the exotic copper, the fanglomerate pieces, chrysocolla and chalcocite that clearly were coming off of a porphyry copper system that nobody's seen before because it's buried. So our objective was get down under the gravel and find out where this copper was coming from. I won't go into the details of the magnetotelluric anomaly. You heard that. Okay, so in October, we started drilling our drill hole BS1, a core hole. We drilled through a lot more gravel than I had ever anticipated we might, 890 meters, 2,900 feet. But underneath that gravel, and really what kept the hole going was that with each run, we would see pieces of porphyry copper in the gravel. You'd find A veins and B veins and D veins as cobbles and boulders in the gravel. So it was clear we were very close to the source of those boulders and perhaps even right above it. And by pushing the hole down to bedrock, we found that we were actually right over the top of kind of the inner edge of the propylitic environment of a porphyry copper system, the inside of the green rocks environment where chlorite butts up against sericite in the model. The things we saw in the core were Gaussian veins. Clearly there used to be a lot of sulfide in that leached cap that we initially drilled into. We see goethite, hematite, jarosite, native copper, sooty chalcocite, coating pyrite, covalite, sphalerite, galena, and quartz molybdenite veinlets. So it was clear we drilled a porphyry copper system with the first hole, drilling issues, and just not really wanting to keep pushing the hole down in a sub-economic part of the porphyry led us to terminate that. But it was right around December when we drilled into this thing, and we rushed the core down to Nancy, and she pushed it through the lab, and so we got an initial idea of what we're looking at. It's not ore, but it's very clearly a porphyry copper system, and that's what we set out to do. So to find it with the first hole is a real jump start on this exploration project. Here's some of the pictures of what came out of there. This piece here is from 959 meters down the hole. It's chalcocite coating pyrite. It's sooty chalcocite supergene, and we cut what are referred to as B veins, quartz molybdenite veinlets with kind of dusty blue-gray molybdenite scattered through there. chalcopyrite and pyrite on the center lines, sericitic alteration in the wall rocks. This picture shows nice silver gray chalcocite, thickly coating pyrite. This vein was about 5 centimeters wide, mainly a pyrite vein, but encrusted with chalcocite. Here's some of the porphyry that we drilled into that's cut by a classic D vein with a complex sericitic envelope with a center line of pyrite, and this one's got some sphalerite, so zinc sulfide in it. In the meantime, since we drilled that hole, we've learned that we've got a couple of majors for neighbors. There's a ranch on our west side. They've got the best hydrated cattle in all of Arizona. They pump massive amounts of water out of the Big Sandy aquifer and keep their cows well hydrated. We've got another a major copper explorer that's wrapped around us on our south and east side. It got out there through some artificial intelligence exercise and found that there were already claim posts in their AI machine told them to go stake. So anyhow, we went and started drilling our second hole just last week, and we put out a press release yesterday announcing that. Another exercise that we did over Christmas, once we had some porphyry out of the ground, we wanted to test the idea that we had really found a piece of what may have come off of Diamond Joe Peak. So we collected some Diamond Joe porphyry stock, ground it up, and picked out some nice little zircon crystals out of there. These zircon crystals are about 100 microns long. We did the same from our core, ground up some of the core and picked out some zircon crystals. Again, they're about 100 microns long, and sent them off to Paul O'Donnell at the University of Idaho. He dated those very quickly because nobody else was sending him samples because of the COVID virus. Our samples went through his lab real quickly, and he determined that he couldn't tell the difference in age between the two. So the two samples, the Diamond Joe stock and our BS1 drill hole, yielded statistically indistinguishable ages, 74.2 plus or minus 1 and 74.9 plus or minus 1.2 million years. And again, these samples were collected 13.2 kilometers apart, what we believe are different parts of the same faulted porphyry copper system. University of Arizona had dated Diamond Joe back a couple of years ago and got 72.8 plus or minus 3 million years. So their analytical uncertainty was larger, but it still overlaps with the ages that we got from University of Idaho. What's particularly interesting to me is that both of these samples contain contamination zircon, naturally contaminated. As the porphyry pushed up through the surrounding Precambrian wall rocks, it picked up some of their zircons. And both of these samples, our BS1 sample and the Diamond Joe porphyry sample, show the same clusters of Precambrian ages, 1.4 billion years and 1.6 billion years. Supports the idea that they were part of the same intrusion that pushed up through the same old rocks. So we're back out on the ground. We moved a mile, very big offsets. We're looking for a big system, a 5 kilometer by 6 kilometer system. And stepping off 100 meters and drilling again doesn't do you any good, because the system is several miles across. A 1 mile offset, if you're really expecting to find this giant thing, it's a pretty modest offset. So we're out there, been drilling for about a week now, and the hole's going down, and we're seeing a lot of sand. But yeah, we'll know here in a few weeks just whether that big porphyry system extends out under where we're drilling. Well, that's my story. I'm sticking to it, and stay tuned to Bell Copper. We're a Canadian public company. We trade under the Toronto Stock Exchange, Venture Exchange, under the symbol of BCU. Now, thank you for the opportunity to talk, and I'll take questions at this point.
I have a question.
There we go. Okay.
Great. Yeah. That very last slide, you had, I think you kind of joking about the sands, but it looks like bedding is at about what, 40 degrees, something like that?
Yeah, I've measured it around 30.
Well, that was pretty close for a visual guess real quick.
Yep.
Any idea why it's that and not 5 or 10 degrees?
Clearly, there's been some high angle faulting that's rotated it.
Okay.
I've got a question. Any idea on what you think the depth of it is, the deposit? How
Yeah.
much?
I'm sorry, I don't think I got your full question.
I just was wondering if you had any idea what you were guessing the depth would be, where the main deposit is.
Yes, so far the best information I've got, you know, we cut a weak chalcocite blanket at about 920 meters. So it's clear the entire chalcocite blanket probably isn't that deep because we've got pieces of it up on the surface. With that 30 degree dip that you saw in the bedding there, you don't have to go very far, certainly not a mile, before something down at 900 meters comes up closer to the surface. And so, you know, without doing more exploration, I can't tell you if there's some that's within open pit range or whether our target is entirely block cave range. But right now, the answer to your question is about 920 meters, because that's where we've drilled it in BS1.
Okay. And do you see the other secondary mineralization as well, oxides, as well as chalcocite and digenite?
Yeah, we haven't seen any blue or green copper in BS1.
Okay.
Tim, you're going to have to either rename the project or rename your drilling program, because I'm just waiting for the big announcement, and it's all based on BS drill holes. And
I told you at the beginning, right? I'm the liar that Mark Twain warned you about.
well, we're kind of coming up on our hour here, and that was an incredible good talk, Tim. Some real things to think about. You're right, and in that most geologists, you know, don't look at those kind of displacements on these low angle faults, but certainly you've got an awful lot of evidence that you've got, at least you got your toes of your work boots pointed in the right direction. So I personally wish you all the luck, and hope this comes together, and you can call Mark Twain the liar. And unless anybody else has specific questions or anything they want to bring up, I think we're about ready to cool down here. I'm going to turn it back over to Nicolette, and we'll go from there.
Sure. Now, we don't have any upcoming meetings scheduled as far as speakers go. So if you do know anyone who would like to do a presentation to both the SME Maricopa and Pinal sections, just get in touch with me. You can email me at nicolette.taylor@stantec.com. Find me on LinkedIn. We do have an SME Maricopa LinkedIn group, so be sure to connect with us there to see updates. And just, you know, thank you so much to Nancy for sponsoring. We really appreciate Skyline Labs for supporting our SME sections. And of course, thanks to Tim Marsh and his team for preparing this presentation for us today. It was super interesting. So with that, we'll close it out and see you all in future months. Stay safe.
Thank you.
Bye-bye.
Goodbye, everyone.
Bye.
Thanks, Tim.
Bye.
Thanks, Tim.
Bye, thanks.